In this video, I am going to explain the work energy theorem. Actually, work energy theorem is also called as work kinetic energy theorem, which is given by the relation W, which is equal to a change in kinetic energy. As we already know, the change in kinetic energy, which is given as the kinetic energy final minus kinetic energy initial, which is equal to our work done. Now in this video, I'm going to explain how we got this equation. For explaining the concept of the relation between the work and the kinetic energy, so what I'm going to do, I'm going to use the third equations of motion with constant acceleration, which is given by v square, which is equal to v naught square plus 2 into a into delta x. Clear? Now I'm going to explain the concept based on one dimensional point of view, which will be easy for our understanding. So for this, I'm going to use the Newton's second law, which is given by the relation F, which is equal to mass multiplied by the acceleration of the object in x-axis. So here I have to rearrange this equation. I have to reform this equation in terms of x-axis because I'm going to explain the concept in terms of one-dimensional point of view. Now what I'm going to do, I'm going to substitute the value of this Newton's second law here after I make some mathematical arrangement. Understand? So here what I'm going to do, this is our equation. I'm going to multiply half m both left hand side and the right hand side of the equation. I'm going to multiply. Let's I just write multiply half multiply by m in both the left hand side and the right hand side of the equations. So by that, this equation will become 1 over 2 times of m multiplied by v square, which is equal to, I have to multiply this half m again for both term, which is given as half m v naught square plus half m multiplied by this entire term. What is our entire term? 2 multiplied by a of x multiplied by delta x. Now if you see this, we can cancel this 2 with 2, and for this acceleration I'm going to use our Newton's second law, F, which is equal to mass multiplied by acceleration in one dimension. So from this equation, what I'm going to do, I'm going to rearrange this equation in terms of acceleration. Therefore, acceleration of x-axis, which is equal to F over m. Now I'm going to take this, I'm going to substitute this here. So by that, what will happen? Your equation becomes half m v square, which is equal to half m v naught square plus m multiplied by, in this place of x, I have to substitute this f over m. Therefore, f over m multiplied by delta x. Let's we take this delta x, which is nothing but our displacement d. So now what I'm going to do, in this place of delta x, let's we just rewrite this delta x in terms of d. So therefore, half m v square, which is equal to half m v naught square plus this m get cancelled with this m plus f multiplied by d. Now I'm going to move this term to the left hand side. By that, this positive of half m v naught square become negative half m v naught square. So therefore, the equation becomes half m v square. This term will come to the left hand side. By that, it becomes half m v naught square, which is equal to f multiplied by d. So what is this f multiplied by d? The f multiplied by d is nothing but our work done, which we studied earlier. So work done, which is equal to force multiplied by a displacement. Actually, this is d, okay? So force multiplied by displacement, which is exactly the work done. So in this place, I'm going to substitute the letter W. The W stands for work done. Therefore, this equation becomes half mv square minus half mv naught square, which is equal to W work done. Clear? Now, what is this? This is our final kinetic energy. This is our initial kinetic energy, and this is our work done. Therefore, kinetic energy final minus kinetic energy initial, which is equal to our work done. So therefore, kinetic energy final minus kinetic energy initial, which is nothing but our change in kinetic energy. So change in kinetic energy, which is equal to W. Clear? So this is the explanation for getting the relation between the work done and the change in kinetic energy. That's it.